Hi.
Hello, everyone, and welcome to our talk at the Festive Tech Calendar 2023. In our session, we want to talk about scaling in the AKS Wonderland. And before we start, we want to talk about us. So we want to introduce ourselves. So my name is Philip. I'm working at White Duck as a senior DevOps and Kubernetes engineer. I do everything around automation, Kubernetes, stuff like this on Azure. And with me, I have my famous colleague, Nico, who can say some words about himself.
Hey, my name is Nico Meisenzahl. I'm also work at White Duck and basically like Phil, helping our customers bringing their cloud native application to Azure and AKS. So, as said, today we'll talk a little bit about AKS scaling and all the parts included. So briefly, agenda here. First of all, we're starting with the Kubernetes scheduler, sharing them insight, best practices, and so on. Then we're moving over to the Horizontal Pod Autoscaler, having a look at the Vertical Pod Autoscaler, talking about event-driven scheduling with KEDA. And to sum up at the end with the Kubernetes Cluster Autoscaler, so not only about scaling your workload, but also about scaling your cluster itself. And last but not least, pretty new with AKS, we're also talking about the open source tool Carpenter. Yeah, so let's get started. First step, Kubernetes scheduler. So basically, when we're talking about Kubernetes, running containerized workloads, scheduling pods, and so on, basically we need a part of the Kubernetes cluster who does all the scheduling stuff. So basically, Kubernetes scheduler is living in the so-called control plane and is really responsible about managing which pod gets scheduled on which node. So basically, it really decides based on the matrix of the nodes, which node is available, which node has capacity left, and then decides where a pod gets scheduled. So basically, Kubernetes scheduler is basically the key part deciding which node gets any resources allocated and so on. So there's a default implementation. It's called the Kubernetes scheduler. So it's part of the Kubernetes project. This is the default one, but you can swap out if you like. Bring in some custom schedulers, bring on your own schedulers, or also run multiple schedulers in one cluster if you like. So swapping out and running multiple is currently not yet supported with AKS, but it's also a pretty niche setting where you might need those configurations. So we will stick to the Kubernetes scheduler for this talk. As I said, it's the default one. But it's highly customizable and extendable. So you can bring in configuration changes, you can bring in plugins, and then really tweak it as you really require it for your workload. And then basically the scheduling itself is part of a pretty complex part. It's a two-step process. So first one is about filtering all the details, which nodes are available, which nodes have many resources available, and then based on the list of available nodes where a workload could be scheduled based on the request definition you provide in your deployment, for example, then there are more complex scenarios like any kind of ladles, tolerations, and so on. We will talk about this on the next slide, which is basically the second part, the so-called storing process. So what is really important is that the Kubernetes scheduler, also kubescheduler, it's not about scheduling any workload. So it's really a one-time scheduling. Every time a new pod is created, it gets a node, and then basically the workload runs on this node. So there's no integration with rescheduling stuff and so on, though this is not part of the Kubernetes scheduler itself. To get more details, we also included the link to the official documentation here. So talking about scheduling, maybe some details. So what is important? Basically, when there is a workload scheduled in a cluster, the cluster, one of the scheduler decides where to put the workload based on the resource quotas. So it's really important to define request quotas, also define limits, because on the request quotas, then the scheduler can decide, okay, how many resources requires your workload, for example, let's say 1 core or 2 cores, and then basically the scheduler can search for a node which have enough capacity left to then schedule the pod there. On the other hand, you can then decide a little bit if you have a bigger cluster where to run a workload. This can be done by either taints and tolerations, or also with selectors and affinity. So first, taints and toleration, it's basically you tainting your nodes and say, okay, only workload which tolerates those taints is allowed to run on the nodes. So basically doing a deny, and then opting in with tolerations on your workload, saying, okay, for this workload, it's fine to run nodes with a specific toleration. And then you can decide, okay, let's run a specific workload on a tainted node, for example. If we talk about affinity, it's a little bit different. So basically with an affinity, you say, okay, if possible, or you have the option to say, if it's possible, so if there's enough resources available, please run my workload on a specific node pool, for example, or a specific node. And if this doesn't work, it's also okay to run it on a different node. So you have a little bit more configuration options. You can also make it pretty strict, but you have the option to say, okay, if it's possible, run it there, otherwise run it on a different node. And then you can also opt in for any interpod affinity. Let's say, hey, please run this workload next to pods with a specific label. Or you can also bring in some anti-affinity here. Let's say, okay, if a pod is scheduled on node 1 or node A, please don't schedule the other workload also on node 8, for example. So basically, affinity and anti-affinity works here. So basically, tolerations and affinity is about telling the scheduler where to put the workload in best cases. On the other hand, talking about AKS and the availability zones, if you spin up a high availability cluster, it's also important that you distribute your workload and your pods across the availability zones available in a cluster. And this is something which AKS brings out of the box. So if you, let's say, schedule a deployment with 5 replicas, for example, on your nodes are deployed in 3 different availability zones, for example, then AKS will make sure per default or by default to distribute the pods on this specific availability zone and the nodes there. Once again, of course, only if it's possible, if with their resources available and so on. But this is the default behavior. Which can be quite complex is if you have any PVs or disks attached to your node, then you really need to make sure and think about if it's possible to shift a disk from one availability zone to other availability zone, from one node to another node when the workload gets rescheduled. So nearly, I think, around about two years now, we have zone redundant disks which are able to shift around the availability zones because they are synchronized or replicated. But if you have local redundancy disks, for example, then you might getting any issues when you're running nodes on different availability zones, because basically the disk is not able to, let's say, jump to the different availability zone because it's not replicated. And then maybe your workload isn't scheduled because of that. So it can be quite tricky if you have any state, any PVs in your cluster. You should think about that one. Yeah, so these are basically the, let's say, defaults around how a pod workload is scheduled in your cluster. So now let's hop into scaling your workload. First one we would like to talk about is the Horizontal Pod Autoscaler here. So basically, Horizontal Pod Autoscaler allows you to automatically scale out your pods. So let's say you have a deployment, and in the deployment, there's a definition. I would like to have 5 pods. Then Kubernetes normally makes sure that there are 5 pods are running. With Horizontal Pod Autoscaler, you can bring in some metrics and say, based on those metrics, please schedule my workload from, I don't know, 5 replicas to 10 replicas, for example. And then based on the metrics, Horizontal Pod Autoscaler will make sure that those are scheduled as needed. So you have different options here, different metrics. You can go on CPU, you can go on memory. We will do that one in a demo in just a sec with CPU, but you can also rely on any custom matrix, for example. So thinking about you have, for example, an ingress controller or something, and you would like to not scale the ingress controller based on CPU or memory, but maybe open connections or open requests. And then you can, for example, store and this is something you need to do, store those metrics or publish those metrics to the metric server, which is basically the underlying part, providing the metrics in the Kubernetes cluster, Kubernetes environment. So basically push them into the metric server, and then you can also rely on those metrics in the Horizontal Pod Autoscaler, for example. As I said, with AKS or basically any deployment, the metrics are provided by the so-called metric server in the control plane. And basically the metric server collects all the metrics and then propagates it through the Kubernetes API, and tools like Horizontal Pod Autoscaler or any other tools can then consume them. It's basically the same when you're doing a kubectl top pods or top nodes. It's basically the same metrics, which get also provisioned by the metric server. Yeah, and then basically Horizontal Pod Autoscaler supports any kind of scalable resources, so we can use it for deployment, you can use it for stateful set. Maybe there's a use case to really go on a replica set directly, but it really depends on the requirements, and basically everything which is scalable is supported here. So there's something new with Horizontal Pod Autoscaler. It's got introduced in Kubernetes on AKS 1.27, and this now allows that you can scale based on container metrics. So before it was on the consumption of the pod, but if you have pods running with multiple containers, for example, sidecar pattern and so on, you can now really define the metrics on specific containers and scale out based on the metrics on a specific container in a pod, which is also quite helpful. Hey, but now I have a quick demo, and let's see how that works in action. Let me share my demo here. Okay. So basically we already created everything we need, but we can have a quick look. So first of all, we have the configuration itself for the Horizontal Pod Autoscaler here. So this is basically the autoscaling v2 API version we have in the Horizontal Pod Autoscaler here. Just giving it the name and then defining a target here. So we say, okay, please scale the deployment and the name here and the API version. And then we can define, as already said, a minimum and a maximum value here. So we're saying, hey, we would like to scale from 1 to 10, and the metrics we would like to scale. In this case, we're going for CPU, and we're saying, okay, if there's a utilization average of 50, then please scale out. And of course, we need a deployment then, which we described here. So here we have the deployment, just the demo application here, an example with a container and some resource limits and requests, and of course, the corresponding service here. So this is already deployed, so we can do an kubectl get here, and we're seeing, okay, this is our scaling information here, and we're seeing our targets. We're seeing, okay, there's basically 9% CPU based off our 50% we configured. We have the minimum pods again, the maximum pods, and the current replicas deployed here. So we're now also doing an get on replica set and pods. It's basically the same. We have the replica desired one, current one, ready one, and we also have just one pod running here. So basically, as it should be. So what we now can do, let me do it clear here and open up a second window. I will do and watch on the left side. So basically, doing a watch every second new one to really see what's happening, and then doing in the kubectl on so Horizontal Pod Autoscaler definition on the replica set as well as on the pod. So we're really seeing what's going on here. And then on the right side, we will schedule a so-called load generator. So basically just a busybox image doing a curl pretty often, and basically curling our service of the deployment we just defined. And now if you run that one, it will try to curl our application all the time. Now it will take some seconds until we see something on the left side here. This is mainly because we're now basically matrix server needs to collect those metrics. And if those are collected, they need to be propagated to the API. And if this is done, the Horizontal Pod Autoscaler will then be able to decide what to do based on it. So it really takes some time, as you see here, until Horizontal Pod Autoscaler sees, okay, there's something I need to do. It's still, oh, now it updated. You're seeing we have the target is above our definition value, and also some deployments are already triggered here. Basically, we decided between 1 and 10, so it will now scale out if needed up to 10 instances. And now if we wait some time, basically here our count should get down again because of the defined scaling configurations. On the other hand, also some more pods will appear here. Okay. On the other hand, let's continue with the new window here. We can once again do and describe on the Horizontal Pod Autoscaler definition. And we can see all the definition again. We have seen the current values. We're still on 130% here. We've seen the main replica, the max replica, the current deployment. We are still at 3 deployments here. And of course, as you know it from all other resources, we're getting some kind of conditions and also events here. And here, basically, we got an event from Horizontal Pod Autoscaler saying, hey, the new size is 3 because of the CPU resource utilization percentage. So let's go back. Okay, we are still on 3 deployments, so looks like those are fine. So let's skip this here to not further scale out. But this is basically how the Horizontal Pod Autoscaler works. Now, if we stop the requests as we did, we should also see the numbers of pods being decreased. So there's basically already 1 destroyed here. So the count will also go down in some minutes. Yeah, and with this, I would like to give over to Phil to show the next options, scaling with Kubernetes.
Yes, thank you. But can you share the slides, please?
Doing
perfect.
Just 1 sec.
Okay. So as Nico told us, the HPA scales horizontally, so it means it adds more pods. But since September, we have GA, the VPA, which is on the next slide, which is the Vertical Pod Autoscaler. And the difference is that the VPA automatically adjust the resource and request limits of containers based on the actual usage. So what is the benefit of this is that we can use our cluster and the VPA will adjust the CPU memory request used for the workload to their real needs. So often we have under-provisioned or over-provisioned clusters where the scheduler cannot make good decisions and spawns new nodes because we over-provisioned our workload, for example. And so with this, we ensure that our nodes have the correct resources for pod scheduling, and this will help us with cost decreasing scenarios. So we will have less nodes because we are using the resources we already have in a much more better way. How the VPA is working. When installed with AKS, as I mentioned, it's GA since September. It comes with 3 components. It's the recommender, the updater, and the admission controller. The recommender basically watches the metrics of the server from the metrics endpoint, what Nico described, looks at out-of-memory kill events and makes recommendations what is the best or make fair request amounts for this workload. The updater then updates in the workload or in the pod description the requests, and the admission controller is a mutation webhook at the end, which injects these new values inside the pod. So basically, the admission controller on AKS runs in a HA scenario, so you will have 2 replica of the admission controller. Recommender and updater are just one pod inside your kube system namespace with AKS. What are the tips and best practices here? Because then afterwards we're going to look at the demo. It should not be used with the HPA because both are based on CPU memory. That's why you should only use the VPA or the HPA. So you have to decide how you want to scale. And for JVM-based workloads, because there's a limited visibility on how the memory usage of this workload with JVM. Also, one best practice is when you use the VPA, use the pod disruption budget, because when the recommender and the updater update the request resources, your pod will be evicted. So that's that's why you should use the PDB, so that always one replica is available of your workload. And also with AKS, we have a limitation of 1,000 pods per VPA overall. So if you have a really large cluster, VPA is not recommended here. Okay, then let's dive into the demo and make it more clear. I will also share my screen. Okay. Hope you can see it. Basically, I have two demos. One I already deployed. I will describe it later. So what we will do, we will create deployment. Yeah. Then we have a pod called hamster low. And when we make a describe, we can see that we requested 100 millicores of CPU and 50 megabyte of memory. But as this demo is called low, the resources which are requested are way too low for this workload. So what we can do, we can describe our VPA object. So this is the object, as Nico already showed before. It's like the same like the HPA. We already showed more better like here, maybe more clear. We have this VPA object. We have a target. So we define which deployment we take a look at. We have an update policy auto, which is important. So with auto, the VPA will recreate the pod and make it automatically. So that's why we have to use the PDB, because the automation mode just evicts the pod and then it will be this mode, yes. And for the container policies, we set a little bit the limit range. So we say minimum allowed is this one, so 100 millicores and 50 megabyte of memory, and maximum of one CPU and 500 megabyte of memory. So and then we say which resources should be controlled by the VPA, and this is the CPU memory here. And what the VPA will do now, when I close it, we can look at the events with the pods here. As we can see, the low deployment was created. Yeah. In the meantime, it will take some time because the pod is new. The VPA need to fetch the metric server. It will take some time if there are some metrics available. So what we can do in the meantime, we can look at this. My deployment is already there. So we have this. The VPA is already acting. So in this mode here, I set the request way too high. And I set the mode to off. So the VPA will not act on anything, but it will describe some or will show me some recommendations for this high stuff. And it says the VPA high has the mode off, but it's using 587 millicores of CPU and 50 megabyte of RAM. So I can now go there and adjust my requests on my own. With the auto mode, as you saw here, so it will terminate the pods and we'll restart them with the new target resource. We can also take a look at the describe here on the VPA. So we have here the recommendation in the VPA object, and the target value is what is applied in the request now. We will look at this now. The upper bound is what we defined in the VPA object, so it will not go over one core and 500 megabyte of memory. And this is the lower bound. So we said 100 millicores and 50 megabyte, but the VPA decides, okay, the lower bound, the lowest request, what should be assigned is this here. And the uncapped target is a value from the VPA if you don't specify any minimum or maximum values. So then it will do the uncapped target. And what we can do now is we can go and describe any of our low pods. Check in, and we can see that the requests were adjusted by the VPA to this, what you could see in the target here. So in the target object, it said, where was it? It was here, the target for the VPA low. So it adjusted those values for us, and now we are fine. And for the VPA high, as we had the mode to off, we still have our 1 core and 500 megabyte. So it's way over provisioned, as you can see on the recommendations by the VPA. So we could act now and say, hey, let's go and adjust this request, and then from time to time watch what's going on. On this therefore we can use our resources in the cluster way much better than with the without the VPA. So it adjusts the requests to really what is needed by the workload. And with this, I will go back to Nico.
Hey, so let me share the slides again. So, as you see, we talked about horizontal and vertical pod autoscaler, and it is basically around metrics, usage, memory, CPU, also custom metrics, but it's all about basically any kind of usage and then scaling based on that. There's another option, KEDA, which means Kubernetes event-driven autoscaling. And with KEDA, you have the option to scale on events instead of any metrics. This is really, really helpful, even if you say you're doing cloud native development and you're doing asynchronous stuff, for example, putting a message in a queue and then acting on that. And this is where KEDA can really help you. So you can, once again, scale basically any kind of resources which allow scaling, deployments, data set, replica sets, and so on. You can also bring in your custom resources we would like to, so it's just a configuration for KEDA, which resources are supported. And you have really a wide range of supported events. So there are more than 60 scalers, any kind on Azure, any kind of, or the other hyperscalers, and so on. So really basically can act nearly on everything. And this is really great. So it gives you really, really great flexibility, scaling based on event-driven parts. And this is really important that it also allows scaling to and from zero. So you can really build any serverless function-like scenarios here, deploying your application, your workload, scaling it down to zero. And then if there is something, if there is an event, it basically scales up based on your configuration. So you only have the workload running when there's anything to do for it. It also integrates with the Horizontal Pod Autoscaler in the background. So basically, they are also relying on the bases available on Kubernetes. And a really good thing is that KEDA is already there as an open source project for some time now, but now it's also GA on AKS. So it's just one configuration line in your infrastructure as code, and you're ready to go and can just consume it, use it without thinking of installing, configuring, updating all the stuff, which is pretty nice. Yeah, some examples, some ideas what you could do with it. As I said, anything like queues, topics, messages, doesn't matter if it's service bus on Azure, if it's any kind of Redis in a container or so on. Also think about, I don't know, uploading any blobs in the storage container, for example. So there's a new blob and you need to do on something based on this data. So basically, KEDA can scale up every time there's a new blob in the storage container, for example. With the support of Azure Event Hub, you can basically do anything nearly on every event in Azure. And if this is not enough, you can also do something like you may know from Azure Functions, doing an HTTP GET call, calling the application, and then basically KEDA will see it and will scale up, for example. On the other hand, also really nice is you can also use KEDA to integrate it with the Azure DevOps pipeline, with the GitHub Actions, and basically scale your runners, your self-hosted runners, based on the trigger in Azure DevOps, hey, there's a new pipeline run, or on GitHub, hey, there's a new pipeline run, and scale based on these metrics, scale up your runners, do something, run a pipeline, and then shut them down again. So really, really flexible stuff. And here I would also like to show a short demo. So let's go back to my Visual Studio Code here. I already deployed all the baseline in the cluster, but let's have a quick look. So first is we have a KEDA object, scale object here. Once again, providing some metadata information, and then we have an spec block here. And this spec block, we're basically saying the object we would like to scale, and then defining the minimum replicas, maximum replicas. Again, as you said, if you would like to have these serverless Azure function-based parts scaled to 0, otherwise you can of course also stay with, I don't know, 2 instances, 5 instances, and then scale up like you need it. But scaling to 0 is really nice thing here. And then we need to define a trigger. In this case, we define the trigger for the Azure Service Bus here. So we say, hey, here's a service bus. This is the namespace. This is the queue. And please scale up if the queue is bigger than 5, for example. This is really the configuration you require. As you need to authenticate with service bus, we need also provide some authentication details here. And this is basically the authentication reference we're using. This is another resource from KEDA here. And this has a small spec block, and as you see, we're using pod identity here. So Azure Workload Identity, we're providing a managed identity from the background and using that one to authenticate to the service bus. You don't need to care about any connection string secrets, etc. here. So you can just rely once again on the managed identity, workload identity stuff to authenticate with the service bus and to give KEDA the option to check the values, the queue lengths, and so on. And then, of course, we're needing a deployment. This is, once again, as an example. So by this application also looks into the service bus, gets the queue, and then acts on these things in the queue. But we'll show you in a sec. And then down here, we have another secret. So this is basically the connection string for the application itself in this example. Okay. Yeah, so of course you can also get all the details, all the trigger authentication and stuff via kubectl, as you know it with any kind of CRDs here. We're seeing the trigger name, we're seeing that it's the pod identity, Azure workload identity, and if we check shortly the pods here, we do not find anything. And also if you go to the scaled object configuration or describe it, we should also see that there basically currently are no events, and that's completely scaled down to 0 here. Once again, we've seen the minimum count here, all the configuration I just showed you in the YAML. Okay, so let's try to add some work for our deployment. Once again, I'm doing a watch quickly here. So we're doing a watch here on the replica set and the pod. Quickly split it and doing another watch. Oh, sorry. Let's do it this way. So we're doing here a watch on the queue in the service bus and getting basically the count of the messages back here. In this case, it's 0 because we did not create any messages. So let's start up another terminal. One sec. So back, we have 0, 0. And now we're basically running a local application, local.NET application, which basically just creates messages in the message bus. In this case, those are orders. So basically, we are now ordering some stuff in the web shop, and then we have on the other side the web shop proceeding with these orders. So let's run that one. Will take some seconds. Okay, quick issue here. Let me quickly fix that one. Da-da-da. Give me. Sorry. This is the generator.
I could also do it if you want.
Let me see. I think we can. Yeah, but I think I found it. Missed to update that one. So let's try again.
Oh,
yeah. Okay, perfect. So now it asks how many orders we would like to have. Let's say we would like to order 300 pieces here. And now basically the queue is getting added to the order. And we should see the queue now goes up. So we have the 66th in the moment. Now we have 121. And on the left side, you're seeing that pods get scheduled by KEDA because we now have more than 5 messages in the queue. And it should now scale up to 10 if required to process with the work. On the other hand, you're seeing the numbers are already getting down. So we are 260 now. So basically now our order processor processes all the messages in the queue. And then if they are back to 0, also the pod will be scaled back to 0 here again. And you're seeing here the orders are coming and going because every order processes just one message and then it gets scaled up again. I guess some more seconds and we should be back to 0 here. So once again, really nice scaling your workload in Kubernetes, but in this case, not based on any metrics, but based on the queue length in our service bus. Okay. With this, getting back to Phil and the slides. You're mute, Phil.
The old mute trick. Okay, as you saw, we have now shown three options, technical option on AKS, how you can scale your workload. But scaling pods also needs VMs or nodes. So with AKS, typically we have a system node pool, which is exclusive for system pods. Hopefully you do it. If not, then you should do it now. So system pods are for system workload, not for applications that you deploy. Then you have an agent node pool or user node pool called an AKS, and there is our workload. And historically, we said, okay, we want 3, 4, 5 VMs, and then we scheduled our pods there. But this is not cost efficient, is not sustainable. So therefore, we have a cool project. The next is a native project from SIG Autoscaler. It's a cluster autoscaler. I think it's long time available on AKS. Basically, what the cluster autoscaler will do, it automatically resizes our cluster based on demand by scaling nodes up and down. So it will add and remove nodes. As I mentioned or I talked about, is the autoscaler, cluster autoscaler is key when we use HPA, VPA, KEDA, or whatsoever. So we should every time rely on the cluster autoscaler. What does the autoscaler basically do? It watches the kube scheduler, and the kube scheduler marks pods as pending. And then when pods are pending and cannot be scheduled due to insufficient resources, then it will add a new node and schedule the workload there. Yeah, this is one thing. And if our cluster or our nodes are underutilized, it will schedule or mark nodes as unneeded and reschedule the pods so that our cluster will scale back to 1 or 2 nodes. So really cost efficient, and yeah, but it's not really configurable. You can add some configuration there, but it's a basic configuration, and yeah, basically it watches for unschedulable pods. What is the node pool AKS? So the node pool, the user node pool is a VMSS in the background, so the virtual machine scale set. So basically, one limitation is like when the kube scheduler say, hey, I want on this node pool, yeah, then the VMSS will spin up a new VM on the same template where all the other VMs in the node pool. So this is the thing. And the limitation is also you cannot configure the per node pool, so you just have a general config for Cluster Autoscaler on AKS. Okay, then just a quick demo. I think this is not too much to show. Basically, we have a cluster. Again, the same cluster as before. We have some nodes. So we have 2 system node pools where where our workload cannot be scheduled, but we have one node pool workload where everything is going to happen. What we would do, we just run a pod, Nginx pod, but we want 500 replicas. Yeah. So normally, it depends what you're using. The restraints are 110 pods or 240 on AKS. Depends on what CNI and so on, but we don't get in detail. But normally, not one node can handle 500 pods in a default configuration. This is not good. Unknown flag replica. What? Okay, let's make it. Okay. Oh no, there. What happened? Why it does not say replicas anymore? kubectl run does not support replicas anymore. I updated my kubectl. Was a mistake.
That's the issue.
Huh?
So maybe just putting
it
out.
Doesn't matter. Yeah, it doesn't matter. I just grabbed one from here.
Yeah.
Shortly, and just take this one here, make it new. ca.yaml. Paste it here. HPA. I can leave it like this, okay. But I want 500 replicas. I just removed the resources. It doesn't matter. Because that doesn't matter. Okay, then I go back and then I namespace. KN cluster, let's say. Okay, run. Okay, apply -f. Okay. Okay, basically it should now create some pods, and they're all pending, as you can see. There's a long list of pods, and in the meantime, we can see that the cluster scheduler, the cluster autoscaler, will add some nodes soon to schedule my workload. As you can see, some are pending. Let's see, they will change. We can also, in the namespace cluster, we can look at the events. So pod didn't trigger mail up, max node group size reached. So no free slots available. So we have insufficient CPU, and 2 of the nodes have untolerated taint. So the system node pool has the critical add-ons only. But the pod did trigger scale up. Let's see. Some pods should trigger scale up, and as you can see, our node pool 2 are getting bigger and bigger here. So I think I defined 10 max nodes, and now our pods will be scheduled and will handle the workload. And as you see, it will change already. New nodes will pop up and go ready. So that's basically the HPA. Okay, then I think we can, it will take some time, so we can skip it. I mean, you basically understand it. So there's not enough resources, new nodes come up, and your workload gets scheduled. Okay. Then we are already almost finished. Last month there was the KubeCon, and there was something happening what we long waited for. So the Carpenter project was introduced with Azure. So I think also the Carpenter project, which was founded by Amazon, the AWS, is a more granular approach to the traditional cluster scaler. And the Carpenter project was now, I think, given to the Kubernetes SIG Autoscaler. So it's now open source project. I think it was an open source project before, but now it's under the SIG, the Integrated Group Autoscaler on Kubernetes. So you will find it also on GitHub. And what makes Carpenter a little bit different than the Cluster Autoscaler is that it works along with the kube scheduler and acts as a cluster scheduler, basically. Yeah. but you can have more options, and it's watching again for pods that the scheduler has marked as unschedulable. It also evaluates scheduling constraints like the kube scheduler from the kube scheduler, and it provisions nodes that meet the requirement of the pods and not just like in the VMSS, like a template. So it provisions own VMs. And also it reschedules, so makes a collation of all this workload that's running in the cluster and make decision based on the needs of your resources. You will see it maybe on the next slide a bit better, makes it more clear. Can you just go one slide forward? Yes, then we have on the left side, we have the pending Kubernetes pods. Here, some can use the existing capacity, but unschedulable pods will be patched up by Carpenter. So it works along with the kube scheduler, so both leverage each other or need each other. And Carpenter will provision just-in-time capacity for the unscheduled pods, for example, with big requests or low requests. And then the workload can be scheduled, but it doesn't create a VMSS and create a new template. It creates this just-in-time capacity on calculations of what Carpenter does. So to really meets the resources of the workload and not have over-provisioned nodes and the same. So what it also do at the end, then Carpenter will reschedule everything, the existing capacity and just-in-time capacity to, for example, spawn just one node to make it more cost efficient and match everything there. So it will make decisions based on its own calculations. And how you can do it is, when you go one slide better, you define node pools here. And in the requirements, for example, this is one from the Azure project now, you find it on GitHub. We say Arch is AMD 64. We will say Linux. We have a capacity type in the middle. Do I have a... No, I don't have a pointer, but in the middle you see the carpenter.sh/capacity type, which can be on demand or spot. So you can also just spawn spot instances. And the key is the SKU family, where, for example, here for general purpose, it will use any VM which is in the D family, so the general purpose. So you don't say, hey, I use this D4DS standard V5 VM. So you say just, for example, use this instances or this SKU for VMs, and Carpenter will decide which VM it will spawn up based on this key here. So what you specify. And so Carpenter, for this node pool, it's the Kubernetes node pool, but it's not a VMSS then anymore. So it's a VM. And in this node pool, different VM sizes can exist, what is not possible with the VMSS. So Carpenter makes this more flexible, more customizable to your workload needs, which is at the end also more cost effective. And yeah, this is a new tool. I mean, it's can you go back 2 slides? I was skipping some stuff. One more. Yeah, it's available since November, so early stage. So it was announced in the KubeCon. There are at the moment no red docs in the AKS. But you can find the Azure Carpenter project on GitHub, and there's no node upgrade support at the moment. So these are because it's early stage. But it's a promising project, and I'm looking forward to play with it. I didn't have time until today, so that's why we don't have a demo. But as we made the CFP, Carpenter was not available in Azure. That's why we just added it as an extra node. So I'm looking forward to use it. Okay, I think we are at the
Can
end.
sum up, I guess.
Yes.
So yeah, if you now would like to start and scaling your workloads and scaling your clusters, you will find all the slides and demos on our GitHub repo. So just grab the demos there, play in your own AKS cluster, get started with the stuff. Yeah, with this, if you have any questions, feel free to contact us on social media.
Yes.
Write us an email, I don't know, find us on LinkedIn, on Twitter, X, however it's called now. Yeah. And I think let's sum up. Thanks everyone for joining today's session, and I'm saying happy holidays, I guess.
Happy holidays, and don't forget we don't use any third-party tools. This was all AKS built and stuff. So this is really good. So looking forward. And if you have some AKS questions regarding scaling, then as Nico said, just contact us, and we will happy to talk about. Okay.
Bye-bye.
Bye.